Again, my numbers are completely backwards from what I understand the theory to be. So I found this great video online that talks all about Graham's law of effusion and diffusion. It also relates a little bit to how Dalton's law of partial pressures works. And yes, I did do a video about this, but not exactly. I started out with that in mind, but I made the mistake of using latex balloons, which have all sorts of other properties that affected the way that the gases were diffusing through the barrier. But this new video required a tool I didn't have. It required what was called a porous cup. It's basically a porcelain cup with lots of tiny holes in that. And I don't have a porous cup, and I doubt you do either, but you probably have eggs. The thing about eggs is that they're made for growing a baby bird, and unlike us, they don't have an umbilical that connects to their mother, so they have to get oxygen from the air outside of the egg. And that means there are actually millions of tiny holes in the egg that let the oxygen pass in and the used carbon dioxide pass out as the bird grows. So what I'm going to do is make this into my porous cup.
Here's the basic setup. Take a porous cup and attach some tubing to it with a rubber stopper. Connect the other end of this tubing to something that measures the pressure. In this case, a simple U-tube, that is U like the letter U, style manometer. That is essentially a tube with some fluid at the bottom. The only difference is that I'm replacing the cup with an egg and gluing the tubing in. After it's all hooked up, the egg gets put into a container filled with a different gas. If the gas outside is lighter, has a low molar mass, then this lightweight gas will find its way in through the tiny holes faster than the air inside will find its way out. This means that the number of atoms inside the egg will increase, making the pressure go up. On the other hand, if the gas outside is heavier, high molar mass, the air inside the egg will leave faster than the heavy gas gets in. In this case, there are now fewer atoms inside the egg, and so the pressure should go down.
To do this, we're going to need to do what's called blowing eggs. And you need to poke a small hole in the top and a slightly larger hole in the bottom. But before that, I probably should wash this off in case it has any bird goo on it. Right, so after you've washed off your eggs, you're going to want to start by carefully poking a hole in this top side. Gosh, this is harder than it looks. Ooh. About like that. Then you make a larger hole in the bottom. Now, the bottom hole, I'm going to end up putting some tubing in so that I can, again, use this as a porous cup because it's going to get pretty large. So then after you get a big-ish hole, you go ahead and stick something way in there and twirl it up to break up the yolk. Makes it a lot easier to blow it out. And you can tell the yolk's been broken up when it comes sticking out on the thing you stick in there. Then over a bowl, you just blow. And now you have an empty egg. Well, nearly empty. I want to rinse it out. Now, since I'm using this as a porous cup, you see this white filmy stuff here. I don't want too much of that to survive. I'm trying to clear off some of the guck there, to peel out some of that inner film. So set that over to dry and do some more eggs. Ooh. So this one's pretty sturdy. I'm actually going to go ahead and put it into some vinegar because I'm not 100% certain that there will be enough holes for me to get the desired effect. So I was going to dissolve just a little bit of it so that maybe it was going to be slightly more porous. 5% acetic acid. Since this is made out of calcium carbonate, it'll fizz, and I'm just going to do that for 20 or 30 minutes. We'll see, but since I'm right here, I'm going to keep an eye on it. One more of these at least. The pointy end is much harder to do. There's that goop. Okay, so I have these two done here, and this one that I put in the vinegar, the lid out of there. Whoop, come on. There we go. It feels much different. I'm rinsing it off in this kind of outer dark brown is coming off. I'm going to need to glue with good old E6000. I don't want to use hot glue because my tubing is plastic, but I do need these eggshells to be dry. So, it's whistling. There. Then I'm going to glue one of these tubes into the bottom of each one of them. So these eggs here have been drying for a while. To do the next step of this experiment, I'm gonna need to make myself a manometer. Take a different piece of tube, this one's wider around, because later I'm gonna take these ones and squash it into there. Stretch it way out, put some colored liquid down at the bottom, and then that way if I change the pressure on one side, it'll tilt the water and where it balances based on the pressure. What I'm going to do is glue a chunk of this on so it stays. Hold in the middle. There, that's not bad. Now, if the theory behaves correctly, what I should see is not that.
About here is where things started going wrong. No matter what I did, I only saw overpressure, which would have been just fine if all I was using was helium, but I got the same result for carbon dioxide, butane, and even difluoroethane, which is much heavier. At first I thought it was the eggs that were the problem, so I remade them, taking extra care to ensure the internal membrane was scraped away thoroughly. I also soaked one egg for a full hour in vinegar, which turned it all the way white. This still didn't fix the issues I was having. Belatedly, I realized that the temperature had a much bigger effect on the system than the flux of the gas in and out of the egg. Furthermore, I realized that my manometer wasn't sensitive enough. When I was careful to keep the temperature steady and I used a new manometer with a narrower opening, I was able to get a qualitatively consistent result.
Same idea as before, except this time I have the more sensitive manometer. I'm gonna go ahead and do the regular egg, the untreated egg, and do helium. Put the untreated egg. Oh, look at that. That's a very clear response. So now that it is filled with helium, I'm going to take it directly from the helium into the carbon dioxide. And again, you can see now this time with the more sensitive one that this is going lower. The pressure is going down because the helium leaves the egg very rapidly. And that means that the partial pressure inside the egg drops. And when the carbon dioxide then gradually seeps back in, the pressure will again equalize. But you should notice that clearly gas was passing through this eggshell. That's how baby chickens breathe when they are growing inside. There really are tiny, tiny holes in here.
But when I went to try and make the experiment more quantitative, the problems came back. Ultimately, I had to redesign the experiment.
There were so many subtle variations that could affect what was going on, in particular my own body heat, that I kept getting wildly varying results. In addition to that, I didn't have a controlled way of measuring one gas against another. I was either trying to measure the peak of when the helium penetrated into the egg and then the fall off, or vice versa. But I realized after a lot of doing this that that's actually a very complex problem, because as the gas seeps in, the gas inside is now a mixture of gases and has a new molar mass on the average. So I had to come up with a way to eliminate some of those variables. Here's what I actually ended up building. It's 3 parts. So this bottom part here would be the test gas. This would be the one that I would be trying to figure out how fast it diffused through the egg. So up here is where the egg actually is. It still has the same attachment, so I can hook it up to my manometer. But what I would do is this upper chamber is going to consistently be filled with helium every single time. And that's the control gas. And then what I would do is open up the valve, flip it over, and let the heavier gas sink down onto the egg, and the helium would just go up here. If I just measure when the manometer starts moving, and then I measure when the manometer stops moving, that gives me a time for how long it took the gas to diffuse completely into the egg. Since I have a controlled way of measuring this each and every time, I can modify, not really modify, just repeat Graham's law again.
So let's say I'm comparing the first gas. On the top I have the molar mass of nitrogen, and on the bottom I have the molar mass of helium. This equals the rate for helium divided by the gas transfer rate for nitrogen. For the next gas, say carbon dioxide, it's pretty much the same setup, except I replace the molar mass of nitrogen with the molar mass of carbon dioxide and swap the nitrogen rate for the CO2 rate on the other side. Now the trick is dividing these ratios by each other. So the carbon dioxide molar ratio to the helium is divided by the diatomic nitrogen molar mass ratio to helium. Now, using the reciprocal rule for fractions, where dividing is the same as multiplying by the reciprocal, I can flip this one and change this to multiplication. Now the heliums cancel and I'm left with the molar ratio between carbon dioxide and diatomic nitrogen. On the other side, we do much the same thing, and the problem reduces to Graham's law for carbon dioxide and nitrogen. However, we have to remember that the right-hand side is a rate, in particular some volume of gas per unit of time, so expanded it can be written like this. Using the reciprocal rule yet again, the volumes cancel since we're using the same egg each time, and we're left with a ratio of 2 times.
Again, it's just using Graham's law over again, because all I'm doing is dividing the rates of each total mixture. I'm going to hook it up here. The first gas that I'm going to do is just plain old nitrogen, what's in the air. So what I would do normally is I would take this off, fill it up with a different gas, and then screw it on there so I had a sealed chamber where I could keep a hold of that gas for a while. But since we're just doing air, I'm just going to go ahead and leave that one on here. I need to put my control gas in here, that's the helium, so I'm going to unscrew that, and you can see that that's closed right now. Then what I want to do is go ahead and fill the upper chamber with helium. Now, like before, when I do this, you'll be able to see the overpressure of the helium pushing into the egg. While that's still going on, I'm going to go ahead and reattach it up here. One more thing while I'm waiting for this to even out is you might have noticed that my manometer looks a little different. I tried making one here and then a thinner one. What I actually have ended up doing is having a thick tube and a thin tube. What this does is it allows the large surface area on this side to affect the smaller surface area on this side. So the same amount of fluid moves into this thinner tube, so you see a bigger result. This makes my manometer setup more sensitive because that minor change on the right-hand side is going to make a big difference on the left. All right, so my manometer is settled down here. So the steps here are going to be I flip this over, then I open the valve and start the stopwatch. What should happen is immediately we should see an underpressure, that is the helium will leave the egg as the nitrogen rushes to the other side of the container. Nitrogen's up here, helium's down here. I'm going to go ahead and open my valve and start the timer.
So I actually ran this experiment several times. It took me quite a few trials to realize that I needed to run it for about 45 minutes or so for the gases to fully equilibrate, which is why you're seeing this in time-lapse. At about 30 minutes, my timer switches from showing minutes, seconds, and milliseconds to just showing minutes and seconds, but the time that it finally settles on is about 42 minutes and 52 seconds. Hereafter, I wasn't able to detect any more motion, even though I continued recording for another 20 minutes.
This has stopped, the egg is filled with as much nitrogen as going to get there, and that's a good enough time for me. So now for the next gas. So I got to make some carbon dioxide. Now there's a lot of tube here and a lot of volume here, so I really need to make sure that I have plenty of carbon dioxide to work with, which is why I'm doing, you know, something on the order of several liters without spilling my carbon dioxide. Go ahead and screw this on here and trap that carbon dioxide in. Same procedure as before. I need to refill my top chamber with helium where the egg is. Again, this is CO2 at the bottom, helium in the top. Right now these are evened out, which is perfect. So I'm going to go ahead and invert chamber here, open the valve and start. Now what we should see pretty quickly is under pressure. That's what I kept having trouble with when I was dealing with the carbon dioxide before, because I was reacting it, and that meant that I was heating it up as it was being liberated from the vinegar and baking soda. But you can see right here, under pressure, again, exactly as expected, and my timer is going. And if everything goes correctly, I should get a time that's at least a little bit longer than when I just did it with nitrogen. Indeed, the time was longer, about 10 minutes longer. Here it is again in the time-lapse version that I did, and it stabilized at a final value of about 52 minutes and 15 seconds. I continued to record like before for another 20 minutes or so, and I was unable to detect any more variation in the footage after about that time. Now that I have two gases done, I should be able to take the ratio of the two times and have that equal to the ratio of helium to CO2 divided by the ratio of helium to diatomic nitrogen. Since the helium cancels out, this reduces to Graham's law again, with the square root of the molar mass of carbon dioxide, 44 grams per mole, divided by the square root of diatomic nitrogen, at 28 grams per mole, giving us a value right about 1.25. So if I take the CO2 time in seconds, 3,135, and divide it by the nitrogen time in seconds, 2,572, we should get a number at about 1.25 times longer. And 1.21! I've literally been working on this project for months. That was good.
I did do one more gas, difluoroethane, commonly known as canned air, even though it's not air at all, with a molar mass of 66 grams per mole. Plugging this in again to the equation I've set up, canceling the helium masses, I get a predicted rate of about 1.54 times longer to diffuse the nitrogen. The time for this one topped off at about 1 hour, 8 minutes and 30 seconds, or 4,110 seconds. Dividing this by nitrogen diffusion time of 2,572 seconds, I get about 1.6 times longer, which is also pretty good.
This setup, while maybe still not perfect, certainly shows much more closely what Graham's law of effusion actually does. Now, usually you end up seeing the one where you have the different gases on the different volatile gases on opposite sides, and that they progress, and that there's a white vapor at, 2/3 or whatever it is down the middle of the tube. And while that's an excellent demonstration for Graham's law, it's not the sort of thing that you want to do in your basement. If you thought this was fun, I got more experiments on the way. Just go ahead and subscribe and you'll be able to see all of them as soon as they come out. If you want to know more about this particular project, you can visit my blog as usual by following the link in the description or by finding the card on the screen. But you don't have to take my word for it, because you can science it. Tastes like science.